So this is one equation. One is the voltage equation, the other one is the current equation. Why they are called coupled means? So in one equation, in terms of current, it is related to voltage. The other equation, voltage is related to current. Now in this class, we will differentiate these two equations. We will differentiate these two equations again with respect to Z. We will differentiate these equations with respect to Z, and we will see what we are getting. And these equations can be expressed in this way, right? This also we have seen dou Vs by dou Z is equal to minus capital Z. This is minus capital Z into Is. So where Z is nothing but it is called as the impedance. This is called impedance. This is called the impedance. Z is equal to R plus J omega L, whereas the current equation can be expressed in terms of admittance. Here capital Y is called the admittance. So this can be expressed as G plus J omega C. Here R is the resistance per unit length, L is the inductance per unit length, G is the conductance per unit length, C is called capacitance per unit length. So the above equations we can write in this way. Now we will differentiate this with respect to Z, and we will see what we are getting. The same equations we can express in terms of impedance and in terms of admittance. Now we will take this equation. So this is the voltage equation in terms of current. Voltage equation in terms of current. Now differentiate this equation on both sides with respect to Z. Differentiate the above equation with respect to Z. So what we will get if we differentiate with respect to Z on both sides? So this is already having one differentiation. So if we differentiate again, so it will be dou square Vs by dou Z square, right? Dou square Vs by dou Z square, and here it is without differentiation, so we will get dou Is by dou Z. So here it should be square. Dou square Vs by dou Z square is equal to, so this is not having any term related to Z, so this will be as it is R plus J omega L into dou Is by dou Z, dou Is by dou Z. So here it is already having one differentiation, so again if we differentiate, it will change to dou square Vs by dou Z square. So this expression we have, right? So dou Is by dou Z in terms of Vs we have, right? What is that expression? Minus dou Is by dou Z is equal to G plus J omega C. This is nothing but the admittance capital Y into Vs. Now here in place of dou Is by dou Z, we will substitute this here in place of dou Is by dou Z. So we will substitute this expression. So if we substitute this expression, so this equation is already having one minus, and dou Is by dou S is also having one minus. So this minus and this minus will get cancelled. Now this will be multiplied by R plus J omega L into G plus J omega C into Vs. So earlier this equation is Vs related by Is. Vs is related by Is. So if we substitute this in the above this equation, we will get this equation. So here also it is square. Dou square Vs by dou Z square is equal to R plus J omega L is as it is. So this is G plus J omega C into Vs. Now on both sides of this equation, the second order differential equation, so both are same parameters. So here on the left hand side also we have the voltage term, and the right hand side also we have voltage term. Whereas in the first order differential equation, on the left hand side we have voltage term, whereas on the right hand side we have the current term. Whereas in the second order differential equations, both sides it is related by the same parameter. So that is the difference between first order differential equation and this second order differential equation. So here this is nothing but capital Z, right? This is nothing but capital Z. So whereas this is nothing but capital Y, capital Y. So dou square Vs by dou Z square, we can write it as capital Z into capital Y into Vs. So this is the second order differential equation, whereas this one is the first order differential equation. So is it clear? So simply we have to differentiate this equation, and in this equation we have to substitute for the dou Is by dou Z in terms of Vs. Now this equation, the entire equation will be only in the same parameter. On the left hand side also we have the voltage term, on the right hand side also we have the voltage term. Whereas here left hand side we have voltage term, whereas the right hand side we have current term. So that's why this equation is called coupled equation. This equation is called coupled equation. But here it is not the case. On both left hand side and right hand side we have the same parameter. Now we will take the other equation. Now we have taken dou Vs by dou Z. Now we will take minus dou Is by dou Z is equal to Z plus j omega C into Vs. That equation we will differentiate. So now we will take this equation, we will take the another equation. So this we can write in this way, dou square Vs by dou Z. If you take this to the other side, so this whole term is called or represented by gamma square. So this is the equation that we have. So here also square should be there. Here also square should be there. Dou square Vs by dou Z square. So take this term to the left hand side, and this entire thing R plus j omega L into Z plus j omega C we have represented here in terms of gamma square. Let us call this equation as 5. Let us call this equation as 5. So what is gamma square? Gamma square is nothing but R plus j omega L into Z plus j omega C, whereas this is nothing but capital Z and this is nothing but capital Y. So gamma square is nothing but Z into Y. So gamma square is nothing but this is capital Z and this is capital Y. So gamma square is nothing but capital Z into capital Y. Impedance, this is the impedance part, series impedance part, whereas this is the parallel or shunt admittance part, right? So gamma square is equal to R plus j omega L into G plus j omega C, or we can write it as gamma square is equal to Z into Y. Now we will take the other equation, the second equation, minus dou Is by dou Z is equal to Z plus j omega C into Vs. Minus dou Is by dou Z is equal to Z plus j omega C into Vs. Now differentiate this with respect to Z again. Differentiate this equation with respect to Z on both left hand side as well as right hand side. So if you differentiate the left hand side, what you will get? Minus dou square Is by dou Z square is equal to Z plus j omega C, and if you differentiate this, we will get dou Vs by dou Z. Dou Vs by dou Z. So if you differentiate this, you will get minus dou square Is by dou Z square is equal to Z plus j omega C into dou Vs by dou Z. Now this we know. So substitute in terms of dou Vs by dou Z. What is that equation? It is nothing but minus R plus j omega L into Is. So from 3 minus dou Vs by dou Z is nothing but R plus J omega L into Is. So in place of dou Vs by dou Z, substitute this equation R plus J omega L into Is. So here also minus and this minus will get cancelled. Now this will be Z plus J omega C into R plus J omega L into Is. Now both left hand side and right hand side now will have Is similar to the earlier expression. So minus, sorry, dou square Is by dou Z square, and this we have seen. So this is nothing but capital Y Z plus J omega C is nothing but capital Y, and R plus J omega L is nothing but capital Z. So we have already represented capital Y into capital Z is nothing but gamma square. So if you substitute this here and if you take this term to the left hand side, we will get dou square Is by dou Z square minus gamma square Is is equal to 0. Let us call this is the sixth equation. So now the second order differential equations on both sides, and it is entirely of the same type. So it is having the current expression. So whereas here the first order differential equation, on the left hand side we have the current, on the right hand side we have the voltage. So first order differential equations, the voltage and current are coupled. So whereas here it is not coupled, it is decoupled. So these equations are called decoupled equation, whereas here it is coupled equation. So second order differential equation, we have only the same terms, both current or voltage, whereas in the first order differential equations, so on the left hand side we have one parameter, on the right hand side we have the other parameters. So that's why the first order differential equations are called coupled equations, whereas the second order differential equations are called decoupled equations. So these are the equations, the second order differential equation. On both sides we have the same parameter. So the equation is containing the same parameter. So gamma square, what is gamma square? Gamma square is nothing but R plus J omega L into Z plus J omega C. So this is nothing but the capital Z, and this is nothing but the capital Y. So what is the similarity means with respect to the first unit equations is, in the first unit also we have seen wave equations, right? We have seen wave equations, right? So these equations are also similar to the wave equation, except in wave equations, in terms of voltage we will have the electric field. In terms of voltage we will have the electric field, whereas in terms of, in place of current we will have the magnetic expression. So if you look back at the wave equations for the plane waves, so there also we will have this type of equation, but only difference is in terms of voltage. In terms of voltage we have the electric field intensity, whereas in case of current is replaced by magnetic field intensity. So that is the only difference between the wave equations that we have obtained for the voltage and wave equations that we obtained are the transmission lines. So these equations we have derived for the transmission lines. So these are called wave equations for the transmission lines. So whereas in the first unit we have derived, those are called wave equations for the plane waves. Both are having the similar form. Only the difference is here in place of voltage, there for the plane waves we have electric field, whereas in place of the current we have the magnetic field intensity term. So the solution also will be similar to the wave equations for the plane waves. Wave equations for the plane waves. Solutions will be similar. The second order differential equation solution, it will look like in the same way. So these are the wave equations for the transmission line. These are called the wave equations for the transmission lines. So now we have seen their gamma is called the propagation constant. So gamma square is given by r plus j omega l into z plus j omega c. So this is capital Z and this is capital Y. So if you take square root on both sides, so here we will have gamma. Gamma is equal to square root of z into y. So this gamma is nothing but the propagation constant. So there also we have the propagation constant. So here also we have the propagation constant in the transmission line. So it is equal to root of z into y, where z is nothing but r plus j omega l, z plus j omega c. So here this is also complex quantity. Z is complex quantity and Y is also complex quantity. Both are complex quantities, right? Both the terms are complex quantity. So gamma, the propagation constant, is also a complex quantity because Z and Y individually they are complex quantity. So gamma is also a complex quantity. We can express alpha plus Z beta. Alpha plus Z beta similar to the we have expressed. So gamma is a complex quantity because Z and Y are complex quantity. So gamma we can express as alpha plus Z beta. What is alpha? Alpha is nothing but the attenuation constant. Alpha is nothing but the attenuation constant and beta is called the phase constant. Alpha is called the attenuation constant and beta is called the phase constant. So the expressions will be somewhat similar to what we have seen in the for the plane waves. So but it will be here in alpha and beta will be in terms of r, omega, l and g and c. So that is the difference. So there it will be in terms of epsilon and permittivity. Epsilon and permittivity. But here they are in terms of R, L, G and C. So alpha is the attenuation constant and beta is called the phase constant. So gamma is a complex quantity because both Z and Y are complex quantities. So gamma is called the propagation constant and alpha is called the attenuation constant and beta is called the phase constant. Now the wavelength we can obtain. Wavelength from the phase constant we can obtain by dividing 2 pi with beta. We will get the wavelength. Wavelength of the corresponding wave equation of the transmission line. So by dividing 2 pi with the phase constant, that we will get from the propagation constant. So we can get the wavelength of the wave equation of the transmission line. And similarly wave velocity will get if you take the ratio between the omega and beta, if you take the ratio between omega and beta, we'll get the wave velocity. We can denote by u or it depends on the representation. So here we are representing with u. The wave velocity is represented with u. It is nothing but the ratio of omega by beta. Omega by beta. So if you express omega in terms of 2 pi f, omega we can write in terms of frequency as 2 pi f, and from here you can write beta as 2 pi by lambda. So from here you can write beta as 2 pi by lambda. So if you substitute beta in terms of lambda, so 2 pi will get cancelled, we will get f lambda. So the wave velocity in terms of wavelength is given by f lambda. So f is nothing but the frequency of operation at which we are operating. So this is the wavelength and this is the wave. So wave velocity we can express omega by beta or f into lambda. Wavelength is nothing but 2 pi by beta. 2 pi by beta. Now we will see what is the solutions of the transmission line equation. So these are called the transmission line equations. Now what is the solution of this equation? So these are the second order differential equations that we know, well familiar with the second order differential equation. What will be the solution? It will be e power minus gamma z will be one solution, and e power plus gamma z will be the other solution. So these are linear homogeneous differential equation. So the solution for the voltage we can write as Vs is equal to, as it is a second order differential equations, we'll have two roots. We'll have two roots in terms of one is plus gamma, the other one is the minus gamma. So Vs is equal to, we can write it as V plus, this is a constant, and V minus is also a constant. So if you substitute the conditions, initial conditions, we will get the expressions for V plus and V minus. If we substitute the initial conditions, we will get the expressions for V plus and V minus. So this is one root, this is the solution corresponding to one root, and this is the term related to the another root. As this is a second order differential equation, so here also it is z square dou square Vs by dou z square minus gamma square Vs is equal to 0. So this is the one solution. Vs is equal to V plus into e power minus gamma z plus V minus into e power plus V gamma z. So as we have already seen, so this term is corresponding to the wave propagating and in forward direction. Forward direction or plus z direction. So this is corresponding to the reflected wave or wave that is propagating in the minus z direction. So this is related to forward wave, whereas this is related to reflected wave or traveling in negative z direction. So whereas this term is related to the wave forward traveling or plus z direction. So this is the solution of a linear homogeneous differential equation. So gamma, we know that gamma is nothing but alpha plus z beta. So if you substitute in place of gamma, alpha plus z beta, alpha plus z beta, and if you separate e power minus alpha plus z beta, so this you can write it as e power minus alpha z and e power minus z beta z plus V minus. So here also if you substitute in place of gamma alpha plus z beta, so this will be plus V minus e power alpha z into e power minus, sorry, e power plus z beta z. Simply in place of gamma we have substituted alpha plus z beta, and we have separated this term e power a plus b, we can write it as e power a into e power b. So e power a plus b we can write in terms of e power a into e power b. So by using that substitution we have separated the terms in both the terms. So the factors v plus and v minus are also complex quantities. The factors v plus and v minus are also complex quantities. We will see why it is the case. So as I have said, e power minus z beta z, e power minus z beta z, this term is a wave traveling in the positive z direction. E power minus z beta z is the wave traveling in the positive z direction, or it related to the forward traveling wave, whereas e power j beta z, e power plus z beta z will be the wave traveling in the negative z direction or the reflected wave. So this corresponds to forward wave, this corresponds to forward wave, This corresponds to backward wave or reflected wave. Backward wave or reflected wave. So e power minus j beta z is corresponds to wave traveling in positive z direction, or e power plus j beta z is the wave traveling in the negative z direction. And beta z, the product of the phase constant, beta is called the phase constant, right? Beta into z is called the electrical length of the line. So this term beta z is known as the product of beta into z is called the electrical length of the line in case of transmission line. So this we will refer later. We will use beta z. Beta z is nothing but the electrical length of the line, and units are radians. So beta units are radians per unit length. So z is nothing but the distance. So unit length and both lengths will get cancelled. So we'll have only the radians. Beta z will have the units of radians. Beta z is nothing but the electrical length of the line. So its units are radians. So e power minus j beta z is corresponds to the wave traveling in positive z direction or the forward wave, and e power plus j beta z is the wave traveling in negative z direction or the wave reflected or backward wave. Similarly, for current, this is the solution corresponding to the voltage. Now we will see the expression for current. So it will be also similar to the voltage. So in place of V plus, we'll have I plus, and in place of V minus, we have I minus. So these are the constants that we can find by substituting the initial condition. So this is I plus and this is I minus. So these are nothing but the constants we can find by substituting the initial conditions. So these are constant. We can find them by substituting the initial condition. So these two equations are called the solutions of the transmission line equation. So these two equations are nothing but the solutions of the transmission line equation. So one is for the voltage, the other one is for the current. So these two equations are called the solutions of the transmission line equations. So now if you want to express in terms of z and in terms of t, in terms of z and in terms of t. So this is this type of expression. If you express in terms of z and in terms of t, that expression is called the instantaneous expression. Why it is called instantaneous? At any instant, at any distance, or at any time, at any distance, at any time you can find the voltage or current. So that's why this expression is called instantaneous expression. Instantaneous expression. So that we can get by taking real part of. So these are nothing but. So these two equations are in terms of z. So here Vs is depending on z, right? Depending on z. Similarly, this is also a function of z. Current is also a function of z, because here on the right hand side we have, it is the distance term. So by multiplying e power j omega t, if you multiply Vs of z with e power j omega t, and if you take the real part of this entire term, if you take the real part of this entire term, you will get the instantaneous expression. So if you substitute Vs of z here, right? If you substitute Vs of z here, you will have V plus e power minus gamma z plus V minus e power plus gamma z, and multiply with e power j omega t. Substitute and find the expression. What is the expression that we are getting? So in place of Vs of z, you substitute this expression, V plus e power minus gamma z plus V minus e power plus gamma z, and multiply with e power j omega t. E power j omega t. and take real part of that. Take real part of that. So you will get this equation v plus e power. So in place of gamma, you have to substitute, in place of gamma, substitute alpha plus z beta. In place of alpha, you substitute alpha plus z beta. In place of alpha, substitute alpha plus j beta. So it will be e power minus alpha z and e power minus j beta z, and you have to multiply with e power j omega t. So e power minus alpha z term will come outside, and we have the complex term e power minus j beta z into e power j omega t. So if you take e power j as common, if you take e power j as common, you will get omega t minus beta z for one term. If you take e power z, if you multiply e power minus j beta z and e power j omega t, and if you take e power j common, it will be omega t minus beta z. And real part of this is nothing but cos term. Real part of e power j theta is nothing but cos theta. So cos of, we have omega t minus beta z. So similarly here, you substitute in place of gamma alpha plus j beta, and if you take e power j common, you will get omega t plus beta z. So this is the instantaneous expression for the voltage v plus e power minus alpha z cos omega t minus beta z, and v minus e power alpha z cos of omega t plus beta z. So this minus n, or here this minus n, it will indicate the wave traveling in positive z direction or forward wave. So whereas this corresponds to the wave traveling in minus z direction or the reflected wave. So in this equation, we will have both forward wave or the positive z direction and reflected wave or the wave traveling in negative z direction. So similarly, for current also, you can write the same expression. So what is the change? Only in place of v plus, you will get I plus. In place of v plus, you will get I plus. And similarly, in place of v minus, you will get I minus. Rest of the expression is same. I of z comma t also you can write in the similar way. I of z comma t also you can write in the similar way. Only the difference is in place of v plus you can write, you have to write I plus, and in place of v minus we will write I minus. So any doubts so far? So in this class we have started with the equations, and then we find the solutions for the transmission line equations. So we have started with the equations, coupled equations, and then we have seen the solutions for the transmission line wave equations. We have started with the coupled equations. In coupled equation, on the left hand side we have one term, on the right hand side the other term, and then we have seen second order differential equations. Those are decoupled equations, and we have find the solutions for the transmission line equations. So the next one is the characteristic impedance. Characteristic impedance. So this we will see in the next class. So this is called the characteristic impedance. So that we will see in the next class. So in this class,
if you like the video, please share, like and subscribe. Hit the bell icon to get latest video updates.